Okay, now if you stretch out a good spring, and let's call this an ideal spring behaves in this way exactly, and the ideal spring also has no mass. Now there's no such thing as an ideal spring, but we think in terms of the ideal, and then we modify that for reality. And we're not going to do much modification on that until maybe we encounter it in lab, and likely much later in the semester. But we want to get this idea, okay? So, if you pull the spring back, it exerts a force in that direction. So if I pull this way, the force in this direction keeps increasing. And that force is a linear function of how far you pull it back. And as a matter of fact, it's going to be a proportionality. If x is measured from the equilibrium state of the spring when there's no force acting on it. Okay. In that case, the force of the spring is negative kx. If then the force of the spring is negative 12 newtons when x is 4 centimeters, that means I pull this thing out 4 centimeters, about that far, and it exerts a force of 12 newtons that way. Okay, and 12 newtons is, between 2 and 3 pounds, closer to 3. So it's not a huge force, but it's, that makes a relatively stiff spring. Okay, if this is what happens, then what's the value of K? Well, that's very easy. Put in negative 12 newtons for the force and 4 centimeters for x. You find that negative 12 newtons is negative K times 4 centimeters. You easily calculate K, and you find it's 3 newtons per centimeter. Okay. Now, what's the average force then exerted on a mass attached to a spring? So you attach a mass to this spring, and you pull it back 10 centimeters, and you release it. Well, now if there are no other forces acting, the spring is going to accelerate this mass back. And what will the velocity of that mass be when you get to the 5 centimeter position? Well, using this energy idea, it's very easy to answer that question. Okay? The average force from 10 centimeters to 5 centimeters, well, at 10 centimeters, you plug that in with K equal 3 newtons per centimeter, you get negative 30 newtons. Plug in x equals 5 centimeters with K equal to 3 newtons per centimeter, and you get negative 15 newtons. So, the force being linear means that the average value of the force on that interval is the midpoint, or the average of these two, and that turns out to be negative 22.5 newtons. Now, what's that do to the object, and where in the world is the board where I calculated that? Well, okay, you get that. Now, from this average force, you multiply that by your displacement. So, a little sloppy, but that never bothers me. So I'm going to come over here and work that. So your delta S and you could call that delta X if you wanted to. Anyhow, it's negative 5 centimeters. Now your F net times your is going to be negative 22.5 newtons times negative 5 centimeters, which is going to be, I think, 112.5 newtons times centimeters. Okay, now, this is not in a consistent set of units. It's not in SI units. We could change that to newtons times meters. A meter is 0.01 100th of a centimeter. So we could say this is 1.125 Newton meters. Okay, so we've got our F net delta S. We can set that equal to the change in 1/2 mv squared, if we know the initial velocity, and find the final velocity. So I think that I've done that, I just don't see it. So I'm going to kind of search that out and talk about it in another video. Either that or I'll just get a clean board and talk about it there.